Hi, I'm Debbie Saunders from Wildlife Drones, and we've developed a robotic radio tracking drone to help researchers and land managers radio track animals more efficiently. Radio tracking is undertaken around the world on a wide diversity of species, and although we have an increased ability to track large animals using satellite and GPS tags, radio tracking small animals is often the only option and remains the most reliable and valuable way of studying small animal movements, as well as for studying animals that move in dynamic ways or inhabit remote or rugged areas. Having said this, one of the biggest challenges when radio tracking is when they move large distances in unpredictable ways beyond the study site, such as during dispersal, breeding, or when they just go AWOL for a reason that we don't understand. Or sometimes they inhabit areas that are really difficult to access. In these situations, researchers currently need to take extreme measures to track down the missing animals, from jumping in a canoe to climbing up on top of anything they can from the nearest mountain to a car or a fence, or going into a helicopter or light plane and precariously hanging out the side searching for a signal, or alternatively getting increasingly large teams of people to scour increasingly large areas of the landscape. This is all very labour-intensive, expensive and time-consuming. The other downside to manually tracking on the ground is that you can often disturb the behaviour that you're trying to study, as well as damage the habitat. By continuously traversing the habitat of the animals, you can trample the vegetation which provides the cover that they need to be safe, and encourages encroachment of feral predators such as foxes, increase the predation of these animals within their natural habitat. In addition, within rugged and dangerous landscapes, it can be prohibitive to radio track in these areas. Just the sheer effort and logistics required to get into a rugged terrain like this really is prohibitive. And in tracking areas where there's crocodiles, the human safety factor is quite paramount. So in these areas, it really is quite difficult to track the animals that you're trying to study. It's also prohibitive to manually radio track the movements of animals that undertake dynamic or highly variable movements, such as the swift parrot, which is a key focus of my research. So far, our work on this species to date has shed significant light on the areas that provide habitat for them. However, it remains a mystery how they get from their breeding area up to their non-breeding areas each year and going to different locations. No one knows how they get there or what area do they need to use in order to sustain themselves throughout the winter. To give an indication of the variability of their winter habitat use between years, you can see three maps here, indicating where the population concentrated in 3 different years. In one, they concentrated in central to western and northeastern Victoria. In the second, they're more concentrated in central Victoria. And in the third, they've moved 1,000 kilometres northeast up to the central coast of New South Wales during drought conditions. Given the critically endangered status of this species, it's really important that we get a better handle on the species movements within and between different parts of their range. However, in order to do that, because of their size, we're limited to using VHF transmitters. So we identified the need for a readily transportable aerial tracking system that locates VHF transmitters rapidly and efficiently. However, gaining support for this idea was by no means a quick or simple task. After establishing collaborative partnerships between ANU and the University of Sydney and numerous other organisations shown here, we submitted 3 major grant applications over 3 years. We finally secured some partner funds from Lauro Parker Foundation, and we also were awarded an ARC linkage grant, which meant that over the next 4 years, we undertook extensive research and development to begin translating our idea into a reality. This included designing, developing, and extensive testing for each component of our system, including the antenna, the receiver systems, signal processing algorithms, and robotic algorithms. For the antenna configuration, we developed and tested various different setups, ranging from Yagi antennas, similar to what we use when we're manually radio tracking at the moment, through to monopole antennas, as well as testing out different materials and mounting frames, all of which has various pros and cons. For the receiver system, it was difficult to find a receiver small and light enough to mount on a drone that was also sensitive enough to detect tags as small as 1 to 2 grams, while also having multiple channels so that multiple individuals could be tracked during a single flight. To process the signals and make them meaningful for locating the animals, we had to increase our capacity for rapid and accurate processing with using various iterations of processing filters. We charted a number of different types, ranging from the particle filters illustrated here with the blue dots through to grid-based filters, which are illustrated with the red dots. Both of these filters were used to process the signal phase shift between the observed and the expected radiation patterns of the radio signal. We also developed some robotic algorithms, and we developed and tweaked them in a cyclic fashion until we could maximize the efficiency of the tracking and minimize the time to acquire location information by making decisions and moving around the landscape autonomously. Once all these components were developed and tested in the lab and mounted onto a drone platform that was capable of carrying a 750-gram payload, it was time to head outside and do some field testing to see how it performed in the real world. Initially, we did our tests on an airstrip where we could control the different elements of the environment, and we could focus on the capacity of our system to detect the VHF tags accurately. With extensive trial and error, many adaptations and iterations, we gradually refined our approach and remodeled our system a number of times. Once we could repeatedly and reliably detect signals in this environment, we moved on to the woodland habitat. With our tags launched up in the canopy of the trees using slingshots, we found we were able to rapidly and accurately locate them. Encouraged by this, we then moved on to testing the system on live birds, and we used noisy miners as our demonstration species. In this process, we also demonstrated just how noisy the radio signals become when they're on a moving animal, as illustrated here, where we have the theoretical gain pattern, the gain pattern that you get when you have a static tag up a tree, and the gain pattern you get when you have it on a moving animal. So there's obviously some challenges there in how you deal with these different types of information input. As a result, our current novel system includes a multi-rotor platform with a custom sensor payload, including an antenna, receiver, and microprocessor that uses a 2-point phased array antenna to yield unambiguous bearing measurements. For each step of our system development, there were numerous iterations and technical modifications required, and with each new level of testing revealed opportunities for further development and refinement to increase the reliability and the usability of the system. This, together with the current rapid increase in drone platform capabilities, means that our system is an ongoing work in progress. So how does it work? Well, because we use a small multi-rotor drone, there is no need for a large open launching or landing area. We can simply take the drone to the study site and launch it wherever there is a clearing in the canopy, sufficient enough for the controller to maintain line of sight. It launches vertically to whatever height is specified, and we typically use 30 to 50 meters, so we'll be up above the woodland canopy. The drone then rotates 360 degrees in about 1 minute to collect information from the radio signal at the first location indicated on the map here. It then translates the complex radio signal data received into a display of the estimated animal location live on a Google map, as well as an indication of how accurate it considers it to be. This is calculated based on a model of the expected received signal strength information. Our planning algorithms then incorporate these uncertainty measures to robotically decide where is the next best place to go to maximize the amount of information it can collect, and it moves to the next location marked as number 2 on the map. It then does another rotation, essentially triangulating, and bases the next decision on all the accumulated data. It will continue to do this autonomously until it is either told to return home because the location has been identified, or it runs out of flight time and returns home automatically. With a decent signal and 2 or 3 rotations, you can get a good fix between 10 and 30 metres accuracy in less than around 5 or 10 minutes within a woodland environment. Another application is to simply find out if the animal tags are detectable, in which direction they're coming from, providing a rapid form of check-in for each animal. This can be highly valuable when tracking large numbers of animals or just finding out how your animals are going and making sure they haven't taken off from the study area. There are up to 10 channels for different animal frequencies in the current model, and we can switch between the different frequencies while still in the air. First, as a check to see if all the animals are where you expect them to be, and then you can focus on each individual animal individually. By searching from the air, our current system enables researchers to do an entire day's work of hard labour in less than 2 hours, barely lifting a finger. Because wherever you launch the drone, it becomes a high point. This enables areas to be searched more rapidly and increases the chances of finding animals that move in unpredictable or dynamic ways. It also enables us to minimise the damage we cause to habitat by not traversing right through where the animals are living and trampling the vegetation. It also makes sure that we can minimise the disturbance to their natural behaviour by always specifying the distance that we keep away from the target animal. This would have to be tested for each species being studied, and then you can keep the required distance away so that you can get the best observations of their natural behaviour. With all these capabilities, it also means that we can increase the quality and quantity of data collected by increasing the number of study animals that can be studied in a period of time, or the number of times individuals can be tracked in a day. It also reduces the time and effort to collect accurate location data, meaning that you can free up the time of your volunteers or other staff to increase observational or habitat data collection, or make the most of all that effort while you're out in the field. We've had a significant interest in our system from around the world, with an increasingly fascinating array of potential projects from 18 countries, ranging from tracking orangutans in Borneo so they can be located and evacuated in the event of wildfires, through to rugged and remote landscapes of New Zealand tracking kiwis and kakapos, and to tracking lions travelling large distances across the Botswana savanna. Although some of these animals are able to carry large satellite or GPS tags with remote data download, it has also become apparent that such tags often fail, and researchers need to locate and retrieve the tags using the VHF backup signal. And so this is another application for wildlife drones that can be of value for researchers. If you have any questions or would like to find out more about wildlife drones, feel free to contact us, since we'd love to hear about your projects and how wildlife drones may be able to help you achieve the results you need when radio tracking animals. Thank you.